All right, another great question. This 33. I really like this one. It's kind of like the back one I did in class, where you'll just kind of be absolutely amazed at the numbers and the forces that go on in this structure, in the skeleton structure here. And you can kind of see it here. Why don't I read the question? It says a 75-kilogram man stands on his toes by exerting an upward force through his Achilles tendon, as shown in the figure. So here is FA, the Achilles tendon. So the Achilles tendon, it's attached to the calf muscle up here, and it's contracting, and it's pulling up the heel. And as your heel gets pulled up, it pivots around this joint, whatever this bone is connected to the foot. So this joint between the shin bone and the foot bone, okay? And it pivots. But remember the leverage going on here. And so they're showing a distance of only 4 centimeters out to the Achilles tendon, but to the ball of the foot, it's 12 centimeters. That's 3 times further. So because we're trying to balance a torque here, we're going to see that the force from the Achilles tendon is going to have to be 3 times larger than this force on the ball of the foot. To add insult to injury, this individual is standing on one foot. And so the full weight is right here on the ball of 1 foot. And so whatever this person's weight is, all of it's right here. And then the Achilles tendon is 3 times that much. Wow. And then look at the force right here at the joint. If this is upward 3 times the weight, and here's the weight, that means upward it's 4 times the person's weight. And so the amount of stress here in this joint is then what they call F sub P, the pivot point. So you calculate the force of the pivot of this lever system. This is going to be 4 times the person's weight. That's amazing. Now, nobody expects you to kind of do it like I did it, where you can get kind of a feel for the mechanical advantage. So let's just run through this. All right. I'll start off, though, by pointing out that if you were to take, so I'll take this person standing on 1 foot, give him a knee, give him a little belly, that's terrible, give him a arm, a couple of fingers, head, a second leg, a second knee. Oh, you know what? They've got to be off this foot. So okay. So here is this very weird looking person standing on the ball of 1 foot. And we need to solve for what I would call internal forces in the body, which is the Achilles tendon, and the force at the pivot. But we also need external forces, which is the normal force on the ground. And so let me go all the way back to chapter 4. And that discussion about internal and external forces was very important. If you remember, we had something like this, let's say, and we threw it across the room, and we said it followed a parabola. And we said that even though there might be molecular forces between them, because of Newton's third law, they're equal and opposite, and they cancel off, and the net effect of something in motion always comes from the external forces. Put another way, the internal forces don't come into play, which is good if you don't know them, but it's bad if you're trying to solve for them. So I would say that the key to this problem, and probably why I'm getting people to ask about it, although they kind of help you out, they say the normal force is equal and opposite to the weight. So they kind of give that away, and it probably would be a harder problem if they didn't, because what you need to do first is a free body diagram where you look at the whole body. And that way, if I do maybe a little dot in my free body diagram for the whole body, there is the weight of the whole body pulling down, and the only external force is the normal. And these forces right here that have to do with the Achilles tendon, or this force that's at the joint, this pivot, we don't need those. Those are internal ones. And that way, we can then just say, if you add up all the forces in the y direction, which has to equal to mass times acceleration in the y direction. And again, if you're just standing there, that adds up to 0. And so normal force minus mg, meaning that the normal force is the mg. It is the weight. And like I said, maybe you didn't even go down that road because the author helps you out with what would be the normal force. Or you might even have just a gut intuition. Of course it has to equal to the weight. But I would say if the normal force doesn't always equal the weight. But I did just want to remind you of that whole strategy of internal and external forces. And when you take advantage of it. And so this is a perfect recipe for that, where I'm looking at it as maybe just a foot bone. The foot bone by itself would have external forces of the Achilles tendon and the force from the shin bone on it and the normal force. And I'd have these three unknowns. But if I look at it as a big object, then the only external force is the normal and the force of gravity. And so that's all I need to look at it in terms of a human. Okay, they said that the mass was 75, and so this is going to help me when I do my second free body diagram, because I now know one of the three forces, and that's the normal one. So the normal one is 735 newtons. So I'll say it again, there is some important thinking and creativity in solving this problem by recognizing that fine art of internal and external forces. So I'll say it again, my strategy would be to take the whole human first and do a free body diagram so I can get the normal force. So now my free body diagram will be just the foot. And so I'm going to kind of highlight in green my system. And so when I do a free body diagram, and it's kind of already done for me, there are three forces external to the foot that are pushing on the foot. Notice that there is probably some force between many of these bones. The foot is made out of many, many tiny, tiny bones, and there would be a lot of forces between them. But those would all be internal, so I don't need to worry about those. But external to the foot is, of course, the normal force, but also the shin bone pushing on it, and also the Achilles tendon pulling up on it, okay? And so in a free body diagram like this, I've got three forces. So there's my free body diagram when I'm doing just the foot bone. And I know that this normal one is 735 newtons. That's what I got from my other free body diagram. Okay, so let me just say, why don't I do the second condition of equilibrium? That is, all the torques have to be 0 around any axis. In fact, maybe I'll put it right here. Sum of all the torques should be 0. Now, if you give this some thoughts, and remember that you calculate torque with these two options, RF sine theta or R perpendicular F. If you were to pick, say, this pivot where the bone connects, which is kind of the natural place I think almost anybody would pick. You go, well, that's really where it pivots around. Okay. But remember that torque should be 0 around any point. That's why on the lab, you were asked to calculate the torque around 2 different points, not just the obvious rotational point, but it should be 0 around every point, because if we're stationary, it's not rotating around every point. So the torque should be 0 around every point. Now, if you pick one that's kind of clever, and so notice how you calculate torque, it has to do with R. If you pick a place where the force is actually acting, and so in this case, the force from the shin bone is acting down on the foot bone, the R would be 0. And so you won't get a torque here. And since the force from this shin bone is unknown, it would be very nice if that was not part of the equation. And so the only other pieces I would have would be the force from the Achilles tendon and the force from the normal force. And luckily I know that one. So the only unknown would be the force from the Achilles tendon. So that seems like a good recipe of how we would solve this problem. Pick the real pivot point. You could pick this one where the Achilles tendon is connected, by the way. And that would eliminate the force from the Achilles tendon. And then you would have this unknown force from the shin bone, as well as this one, which we do know when you calculate the torque. So then we could calculate the force from the pivot. But let me not do that. Let me pick what I think most people would pick right away without thinking. They wouldn't bother to say, well, I could do any point because the torque has to be 0 around every point. They would just say, well, this is where it really pivots. This is where the joint is free to rotate. So that's my pivot point. And they would just do that, thinking they would always have to do that. But it's not necessary. But anyways, let's pick that. Because, again, doing the torques, maybe I'd write it this way, that I would have a torque from P, that is the shin bone, a torque A from Achilles tendon, and a torque from the normal. And as I already mentioned, the neat thing about picking this as a point here is R is 0. And so this torque from the shin bone would be 0. Now, from the Achilles tendon, you got to kind of imagine maybe pulling up. That would kind of, if this pin was the foot bone, it would tend to rotate it clockwise. And traditionally, clockwise is a negative. So I'm going to put negative for the torque from the Achilles tendon. And they give me the perpendicular distance as 4 centimeters, or I'm going to put it in as meters. So there's this number, the perpendicular distance, and then times the force of the Achilles tendon. Okay? And then if I looked at the torque from the normal force, which is contacting the foot bone at the ball of the foot, it would have a tendency pushing up to rotate the foot bone counterclockwise. And that's why I'm going to put a plus here. So Achilles tendon has a negative because it tends to rotate the foot bone in the clockwise direction, and a positive for the torque from the normal because it's rotating it in a counterclockwise direction. And then a line of action would come up here, and they're looking at 12 centimeters, which I will put as meters. And then I would get the normal force of 735 newtons. Remembering that's the weight. And so if I kind of move this to the other side, it's 0.04 times the force of the Achilles tendon times 0.12 times 735 newtons. The 2 meters would cancel off. Then I can get the force from the Achilles tendon, and I have 0.12 over 0.04 times 735. This is what I said at the beginning of the problem. 4 goes into 12 3 times, and because of the leverage involved, the force from the Achilles tendon is 3 times the weight. And again, the full weight because we're on 1 foot. That already puts a lot of stress on a foot and a foot bone in the Achilles tendon, because it's double what it normally has. Then you go to stand on your toes, which triples that. And so first 2, because you're on 1 foot, and then tripling that is 6 times. So the force on the Achilles tendon is 6 times the normal weight, and of course that's why bad things can happen when you've got this force. And the body is built to handle that and stand on your toes. But as you get old, or if you have injuries, or if this is an athletic person and they're actually jumping, so the force is even more, this is how you can tear that Achilles tendon real easy. It's just more force than the tendon can handle, and it tears. All right, so according to this, the force of the Achilles tendon is 2,205 newtons. 3 times. And then, of course, part B says calculate the force at the pivot. And as I mentioned earlier, we could go back to a torque and do a torque around this point, and then we wouldn't have the Achilles tendon, and we would get the force from the pivot. But we can also go back to the sum of the forces in the y direction have to be 0, and for that matter, the x, but there's really no point in talking about any x for this problem because there are no forces in the x direction. So this says the force going up, the Achilles tendon, and the normal force, minus the force going down, that's what they call F sub P, that's the force from the shin bone. If you add all those together, you're going to get 0. Or put another way, the force at the pivot is the normal force, which we said is the weight, plus the Achilles tendon, which we said is 3 times the weight. And so together that should be 4 times the weight. But since I actually have these numbers, I'll just put it in. So this is 2,205, and this is 735, and that would be the force on the joint there coming from the shin bone. Now, the shin bone probably could handle that. I'm thinking if anything tears here, it's the huge stresses that are on the Achilles tendon. But you could have something break here, and you could be weak for a number of reasons. Poor nutrition, poor exercise, some kind of disease, and so, osteoporosis, the bone gets thinner and weaker, and even though the muscle's strong enough, the bone just shatters because it does have more force on it than the Achilles tendon. Let's see, 5 and 5 make 10, carry 1, that's a 4, that's a 9, and that's a 2. So 2,940 newtons is the force on that joint. And so hopefully everything's working fine in that joint, all the pieces that work together, and we get a large force, but we don't break a foot or break a shin bone. Okay, hope that was helpful.